Okay, you guys, let's keep going. We are right in the middle. These examples, we did part A, part B. Let's get to C, D, and E. We got a couple of exponential functions. So for part C, we're looking at y equals e to the 5x. Okay, when dealing with an exponential, how do we identify what's outside and what's inside? So it turns out the inside here, there's no parentheses. This is like the exponentials are one of the exceptions, possibly the only exception to the inside function literally being inside a set of parentheses. The inside here is the 5x. Why is that? Because that is in the exponent of e. The e is the outside. The 5x is inside the exponent. So when doing the derivative, y prime, we'll start with the e. Okay, when we do this, the derivative of, remember, the derivative of e to the x is itself, e to the x. So if taking the derivative of e to the 5x, it's just itself for the outside function. The derivative of e to something is just itself, we copy it. But we're not done. Then we have to multiply by the derivative of the 5x, which is 5. So there you are, the derivative of e to the 5x. Well, it is itself, but then you multiply by the derivative of that exponent, which here is 5. So there's your unsimplified version. And if you wanted a simplified version, now you can put the 5 in front. Okay, before we go to part D, I just want to kind of sit on this example just a little bit longer. What if we were asked to find y double prime, the second derivative? Well, let's see. So we'd be starting with y prime. We'd say, okay, there's a constant multiple, this 5, right? So this 5 here would carry over. And then we take the derivative of e to the 5x. This derivative needs a chain rule, e to the 5x times 5. I mean, we just did it. It's the same derivative again for that. So that would tell us y double prime is 25 e to the 5x. Hey, what if we wanted to find y triple prime? Kind of what's the pattern that you start to see? Derivative of e to the 5x, 5 e to the 5x. Derivative of that, 25 e to the 5x. Every time we take another derivative, we're multiplying by 5 again because of the fact that the derivative of the e just copies, and then we've got that derivative of the 5x is 5. So if we wanted another derivative, we'd say, okay, the 25 would come down, this derivative would be itself, but then we multiply by 5 again, 125 e to the 5x. So there's just kind of this nifty pattern when taking multiple derivatives of something like e to the 5x. Okay, just wanted to point that out. Let's go on to part D. Now here we go, e to the tangent 6x cubed. We really got a lot happening here. Before we dive in, kind of take a step back and look and think about what is the inside and what is the outside. Say, well, you know what? Inside a set of parentheses is 6x cubed, but then inside the exponent, there's also a tangent of that. And then there's the e itself. There are 3 layers here. Let's call them the inner, the mid, and the e is the outer. And then it even has a constant multiple that's going to carry along. when doing a chain rule with 3 layers, again, you go from the outside inwards. This one will have 3 links in the chain. All right, let's see how it works. So the 8's just going to copy down, constant multiple. The derivative of this e, we just copy everything. E to the tangent 6x cubed. Okay, there's the derivative of the outermost. Then we move in 1 step for the tangent. What's the derivative of tangent? You might remember it's positive. Its friend is secant. This derivative is secant squared. And it will be secant squared of 6x cubed. So derivative tangent, secant squared, and then this part gets copied. And finally, times the innermost derivative, 18x squared. So there you have it. Derivative of the outer, derivative of the mid, derivative of the innermost. And every time you're copying, for these two, you're copying everything that was, even further within. Some people think of the chain rule as layers of an onion. So you're peeling back each layer, but when you peel back that first layer, you cannot access those deeper layers yet. You got to peel 1 step at a time. And every time you do, right, those inner, what's further in stays until you finally get to it. So here's your unsimplified version. Simplified, what would we do here? 8 times 18. What's that going to be? My calculator, 144. Okay, so maybe we'd say 144x squared, e to the tangent 6x cubed, secant squared 6x cubed. Not a whole lot to really do there for the simplified version. Okay, we got one more. Y equals 7x to the 4th square root x plus 1. Couple things before we get started. First, we want to notice there's a product. Second, the square root, I'm going to rewrite that as 7x to the 4th x plus 1 to the 1/2. And now I can see my product rule. Well, I guess I could already, but now I've really got it set up. When I do the product rule, I'll realize, hey, derivative of 7x to the 4th, no problem. Derivative of x plus 1 to the 1/2. Here I need the chain rule because I've got an inside and then the 1/2 powers the outside. So let's see how this works. Y prime. I'll start with the derivative. I'll start with my product rule is on the outside, or well, that's confusing. My product rule is like the bigger idea. And my chain rule is happening within the product rule. Okay, so product rule says derivative of this, 28x to the 3rd, and I'm going to keep this one as it is. Then I'm going to add, going to keep this part, and now multiply the derivative here, x plus 1 to the 1/2. Okay, so outside first, I'll bring the 1/2. I'll copy the x plus 1, and I'll drop that by 1 to a negative 1/2. There's my outside. Then to finish it off, multiply by the derivative of what's inside the parentheses, but that ends up just being 1. So it doesn't really change much. That's not unusual. We'll get plenty of chain rules whose derivative of their inside is 1. If it's something like x plus a number or x minus a number, that would be the case. And there we go. So there's your unsimplified version. Simplified. Let's see what we can do. 28x cubed. I'm going to rewrite it back as the square root. I could do that. Let's see, plus here, let's see, I've got a fraction. I've got this negative exponent. How about this? I'm going to say 7x to the 4th over, put the 2 down here, and this negative exponent can drop to the bottom, and I'm going to turn it back into a square root at the same time There we go. There's our simplified version, so no more, doesn't have a negative square root in it any longer. And I decided to switch it back to square roots because that was what the original question, they had it in that format instead of the 1/2 power. So I'll switch it back. There you go. I actually find, so later we'll have to, like, you know, set, could even be in this section. Sometimes, you know, we have to set our derivative like equal to 0 and solve. Much easier if things like x plus 1 to the negative 1/2 power are written as a denominator and then even converted back to a square root. It just feels a lot more familiar to most people written in this form. Like if we had to plug in a number, or even especially if we had to, you know, say set it equal to 0 and then maybe solve for x or something. Okay, very, very nice. Let's stop right there.